Welcome. Welcome. Today we're going to talk about the expansion of the universe. This is in some ways the most fundamental thing about cosmology. Our theories of the universe are to a large extent based on this model of the expanding universe. So I'm going to spend quite a bit of time on it, how we came to get to it. I'm going to follow a kind of historical progress because I think that's your way to understand things of how it really developed in astronomy.
Kathy, please mute yourself.
Somebody's got to mute themselves. Theories about the universe really started theoretically. Then we learned how to measure the speeds to galaxies. And then there followed in the 1920s the observation that the universe is in fact expanding. From that, we'll derive the age of the universe, and then I'll talk about something called the knowable universe. So that's the outline of the talk today. Before I do that, I just want to talk about some big numbers. Here, can I get rid of that thing up there? Or?
Yeah, you look okay on that.
You look okay?
Yeah.
And then can I get rid of that?
I think you can slide it out of the way.
No, that's just.
Upper left of the box.
Look at the screen.
No, I don't want to do that.
Go to the upper left of that box.
Yeah.
It looks like there's a.
We'll go right up here. Oh, a little X right there.
I tried that. It's just there. All right, well, it's not going to kill us. All right. So here are some horrendously big numbers. I thought I would try to examine. I estimated the number of stars in the known universe, the part of the universe that we can see. And it's an estimate. So there's a certain density of galaxies. We see one galaxy in roughly every 3 million, then roughly every 10 million cubic light years. There's one galaxy, so that's a density. And I know how big the universe is. We'll talk about that, what we can know about the universe. And I got that on the whole, there are this many stars in the known universe, with 21 zeros, which is about, let's see, that's 10 to the 12 plus 10 to the, it's about 1 billion trillion. Okay. Now I wanted to compare it to something that we're used to, and I estimated the number of grains of sand in all the beaches on Earth, and to do that the same way. You take the size of a typical grain of sand, estimate how many beaches there are, and then multiply that out, and I got 10 to the 20 grains of sand. And you can see, I went to the beach and I looked at it, and for every grain of sand, there's 10 stars in the universe. Wow. And I looked at that and I was just amazed. I mean, even now. Now I wrote 10 to the 19th because after I did that, I actually found something, and some geologists at the University of Hawaii estimated 10 to the 19th. So they're a little bit less than what I got. So, but this is factors of 10 uncertainty. Estimating the beaches on Earth is kind of tricky, and how deep they are, the whole bit. But that's how you do in astronomy. Try to do the best you can based on what you know. And I'm probably within a factor of 10 in both of those. But it could be 10 times more, 10 times less. So those are some big numbers, but even the number of stars in the universe is something that you are somewhat familiar with, namely the grains of sand. I don't know if you ever thought about how many grains there are, but that's roughly what it is. These numbers are astronomical, not to pun. They used to be called astronomical, now they're starting to be called financial. Somebody was talking, but okay. Now I can't estimate for the unknown.
Is that higher or low?
Something is, now my program is hanging up. Well, there it went. Okay. What's happening here? Okay, something else to remind us, I'll talk about this quite a bit, but this is the spectrum of electromagnetic spectrum along the top here. And you can see that we go from all the way from gamma rays to infrared on this, and then if you went even further, it would be into the radio. All those are electromagnetic waves, the same kind of waves, just different wavelengths. Just have different lengths of wavelengths. And the visible spectrum is this narrow region here, the colors that we can see. And it's just that our eyes have certain ranges that they can see. And that is an evolutionary thing. Some animals, like bees, I think, have a slightly different range that they can see. Two of the telescopes we talk about a lot are the Hubble Space Telescope, which looks at the visible and the near infrared, and then the James Webb Space Telescope, it looks at in the infrared. We'll see why later. Okay, well, let me start with how this happened. It really started with Albert Einstein. And you're probably very familiar with the ideas that he worked on, the relativity, special relativity, and general relativity. We didn't work on them. He invented those ideas. And in 1916, he did publish his new theory of general relativity, which was a theory of gravity. Gravity, things that masses attract, and space. And Einstein, when he published it, to see that it was right, he made two applications which were wonderfully corroborated. One is there was the motion of Mercury did not move exactly right according to Newtonian mechanics. There was a slight discrepancy in its motion, but that discrepancy was real. And with general relativity, Einstein got exactly the right answer for it. So that was one corroboration. Second thing he predicted, and this was corroborated a little bit later, but he predicted that, in fact, light would be attracted by gravity. Attraction is not too strong on light, but if, for example, a light beam passed near the sun, it would be bent. And the star position would be different from when the star was not near this in the line of sight to the sun. That was also came out right. He then applied general relativity to the whole universe. And there, how the motion of galaxies. And well, at that time, it wasn't even clear there was galaxies, it was stars, things that people didn't know what those fuzzy things in the universe were. And general relativity, he got the answer out of the theories that he had developed, that the galaxies should move under their mutual gravitational attraction. And they move in the same sense that things on Earth move. If you throw a ball up, it can go up against the direction of gravity, and then stop and come back down again with the direction of gravity, but it's always being accelerated. What you don't see is a floating ball. Balls don't just stop in gravity. Got to move one way or the other. And that was, for the same reason, the result that he got for galaxies. Galaxies ought to be moving. And I'm doing this entirely in terms of galaxies and objects, but we'll later expand this to the idea of space itself. Anyway, Einstein thought that's not right. The stars are just out there. They're not moving. So I think something's wrong with my theory. And so he and everybody else at that time believed that the universe is static. And so Einstein changed his theory to get it to predict a static universe. And he did that, and it turned out it was pretty simple to do that. He added this term which he called lambda, that's just a name, to his equations. And today it's called the cosmological constant. And that stopped the universe. And he thought he'd solved the problem. But a lot of people thought this is a little weird. And the theory predicts the right things for Mercury and for light. Now you're changing it, and it's true that doesn't change Mercury and light much, but seems a little bit spooky. So then two physicists came in and worked on this after Einstein. The first was Alexander Friedmann. And let's see, where am I here? Was a Russian physicist. And Friedmann decided to take the motion of the universe seriously, that had been predicted without the lambda. And he worked out what would happen. And what would happen is exactly as I mentioned. Oh, you can't see that with it. Yeah, that one possibility is you throw a ball up, and it goes up to some maximum height, and then it falls back down. It's accelerating all the time. The other thing is if you threw it hard enough, like you put a rocket on the ball, right, or a rocket, it can actually leave the Earth, never come back. So that's the other possibility. Okay, so those are the two examples of what a ball thrown up could do. And what Friedmann found was that the universe acted exactly the same way. That if you plot now, here on the vertical axis, the distance between two galaxies. I say which two galaxies? I'm saying any two galaxies because the universe is uniform and isotropic, right? So it should be the same anywhere. So if you take two typical galaxies somewhere and their expansion with the universe should be typical, and that could be one of well, three things shown here. One is that it could go up and back down. So the universe could expand and then contract, just throwing a ball up and go down. Or if the initial impulse was strong enough, it could expand forever. And here is the intermediate case, where it's just that it goes from one to the other. That's the middle case. Now, for historic reasons, those are called closed, flat, and open. And that describes some of the geometry of the universe, but I'm not going to go into detail on that. That was Friedmann's result. Friedmann, there's a kind of history of this. I'll just briefly go over this. Friedmann was in, I believe, in Leningrad, and he sent it to a German journal, Nature Science, Nature, for publication, which sent it to Einstein to comment on it. And Einstein said, this is wrong. The math isn't right. And this doesn't work. This doesn't work this way. Friedmann heard that, and then Friedmann.
Oh, okay.
1 gram vaginally twice a week.
Okay.
Every night.
Okay,
Okay.
yes,
All
that sounds
right.
fine. Thank you for letting me know.
You're welcome.
Bye-bye.
Could we ask all the Zoomers to mute themselves to?
Yeah, I've done it, and that
Okay.
was Bonita policing them.
Oh,
Properly.
all right, good enough. Anyway, Friedmann's apparently Friedmann's
Unmuted.
mother came to visit Einstein and persuaded Einstein that in fact the paper was right. And then Einstein made every effort to see that it got published, and it did get published.
Roger,
Friedmann
just
result.
the diagram that you have there, the line that there's a focus of gravity underneath that depending, it's either pulling it down into the closed position or it's escaping to the open position. But if the universe is just this whole analysis, where's the center of gravity?
There isn't a center. It's that every galaxy acting on every other galaxy. So there's no center. Okay. Well, that was there, and then yeah, let me try to explain this a little bit. What we're talking about here with that A, the vertical axis, if just pretend that we have a square grid, and galaxies are at every intersection of that square grid. And then the expansion, the A that we're talking about, is that the A just gets bigger. And that means every galaxy is leaving every other galaxy equally. Now this looks finite and has a center because I can't do an infinite thing on a screen, but that's the way to think about this. So the universe, so he said the universe can expand or contract, but we need observations to tell which. And well, let me go back to the other person who worked on this was a Catholic priest in Belgium, name of Georges Lemaitre. And Lemaitre, unbeknown, he apparently didn't know about Friedman's results, did a lot of Friedman's work, and went somewhat further. He had a fairly detailed model of how the universe should work. And among the things that he did was that he said, if the universe is expanding like this, or contracting, then the velocity that we see of galaxies is going to depend on how far away they are. Because you see, if say you're right here, go over this a couple of times, and you watch then and look at this galaxy, and this galaxy just moved a little bit to here. But if you look at this galaxy, it moved even further. So I'll come back to this again. So Lemaitre predicted that not only was the universe expanding, but one of the things you should see is that the velocity of galaxies should be proportional to their distance. Okay. So those are the conclusions. And again, Einstein objected. Lemaitre sent his paper to Einstein directly. And Einstein made a rather caustic comment saying that your math is pretty good, but your physics is terrible. So was kind of left there. Yeah? Yes?
20, 30 more years ago, I remember there was discussion that the universe was shrinking.
Yeah.
And what was that based on?
I'm not 20 or 30 years ago or 40 years ago, the big controversy was the universe in steady state. Well, okay. Everybody could see that the universe was expanding, but it might shrink in the future. If the mass, right, it could turn over. But all of us, here we are with this again. No, I can't see how can I get to the, wait a minute here, yeah. I have the wrong glasses, so it's.
Three button on the far left of my.
No, I need to go on
To full screen.
full screen.
Green button there. Green button in the.
Oh, okay. No.
The green button, they're right to your left. My left. There it is.
There
Try
it is,
that.
green button right there.
No, right
See, 20 or 30 years ago, everybody realized we were expanding. But what the future would be was not clear. And Alan Sandage spent his whole life saying that, trying to figure out which it would be. And I even remember an incident. I didn't actually see the incident itself, but people said Alan Sandage had been working for 20, 30 years trying to figure out which of these was true. And somebody said, look, Alan, you're never going to do it in your whole life. We'll never figure this out. And Sandage got really angry at that.
Go to play,
What do I have to do with it?
because you got this. stuff
Oh.
here. Good,
All right.
good.
Okay, the next step was an observational one. This was the situation in 1927. Theoretical, not too well known, but the next step was by three astronomers. The first one was actually Vesto Slipher, who looked at some nearby galaxies. And of the sort of 10 nearby galaxies that he could do at the time, he found an odd result that 8 of them were actually leaving us. And now how do we do that? So we figure out the velocities of galaxies from their spectra. So we send the light from a galaxy into through a prism or through a diffraction grating and get the spectrum. And when you look at the spectrum of a star, you see the rainbow. That's because the raindrops do the same thing. They disperse the light. But if you looked with an instrument, you can't see it with a naked eye, but when you look at an instrument, you see these lines, these black regions. Now, what the lines are in an instrument like that, there's a narrow, you put the light through a narrow slit. You see here, the light has to come through a narrow slit. You can't illuminate the whole thing. And the black lines are images of that slit where there is no light from the sun, if there's a solar sun or a star. And those are specific wavelengths at which atoms in the atmosphere of the star absorb light. The hydrogen absorbs light at certain wavelengths, calcium at other wavelengths, nitrogen at other wavelengths. And so those are the things that we see. We see those frequencies. And here's another spectrum. This is now of hydrogen. Hydrogen has a particularly simple spectrum. But what happens with a lot of galaxies is that the spectral lines are shifted to different wavelengths from what we see in the laboratory of hydrogen here. And the way to think of that is a Doppler shift. You're all familiar with Doppler shift. When a siren comes toward you, it's at higher frequencies. When it's leaving you, it comes in at lower frequencies. That's the famous Doppler shift. And light does the same thing, except our eyes can't detect it. But instruments can. So the Doppler shift, so that is an indication that the galaxies are moving. By the way, I learned that for the Doppler shift of sound, there was a wonderful experiment. Apparently, nobody knew about the Doppler shift of sound before the 1830s, before trains came in. Nobody had ever traveled at 30 miles per hour or 40 miles per hour before. So nobody had noticed the Doppler shift. And Doppler, a Danish physicist, I think, claimed that, in fact, the frequencies are shifting. And he did this wonderful experiment. He had a train, literally a big train, and he put a lot of trumpeters on one of the cars, and they could play a perfect A note with the trumpets. And he had people on the side of on the ground listening as the train went by, and they played, and the sound did shift. That proved it. So I thought that was a wonderful experiment. I would have loved to have seen that. Okay, well, so it is the same thing happens with light because it is also a frequency property. It has a wavelength, and that wavelength shifts as it comes towards us or leaves. But we don't see, when the fire engine leaves us, it isn't redder. It's because our eyes can't detect the small change that happens. And so Slipher, go back, where did I have it? So Slipher was the first to try to measure this effect. And he could only measure it for very nearby, very bright galaxies. And he noticed that 10 of them were, of the 10, 8 of them were leaving us. 2 were actually approaching us. Andromeda is approaching us. And he was a little puzzled by that, but it could just happen. Then Edmund Hubble got onto this project after he had shown that Andromeda and the galaxies are outside our galaxy. Edmund Hubble got onto this problem, and he worked with Milton Humason. And Humason doesn't get much credit for this, but he was apparently, I think, a technician and helped Hubble, but he became such a good observer that he did much of the observing, the work that Hubble did. So Hubble and Humason worked on this, and Hubble discovered that the galaxies are by and large receding from us. This is a picture from actually Hubble's book called The Realm of the Nebula. And you can see that see, I'm not sure this will show up on the Zoom, but you can see here, it's a negative, and you can barely make it out, but there's these, so this is a negative. This is the spectrum of the galaxy. These lines here are calibration spectra, laboratory to show where the wave frequencies are. And you can see these two, these are calcium lines. And then from a galaxy here, and then from a more distant galaxy, looks fainter here, they're shifted to longer wavelengths. And then for another one, even further, they're shifted even further. So, and then Hubble found that basically almost all the galaxies are just receding from us. Now, there's the couple that are coming towards us, like Andromeda. There is the effect that, you know, the universe is expanding, but I'm not getting further away from you. It's that these local forces counteract that and are larger. But as soon as you get to large distances, the expansion takes over and all the galaxies leave us. So this is a typical picture, which you see in text. I don't think it's actually, I think it's kind of a deceiving picture. You know, you sort of wonder, did we say something or someone or leaving or lactose intolerance? You know, Milky Way, lactose intolerance. I stole that joke from Alex Filipenko at Berkeley, but I think I'll give it back. You never know if a joke's really going to work, you know, but absolute dead science must be telling me something, you know. Okay, so so this is one way to think about it. I don't think it's the best way. The better way to think about it. Why is this happening to us all the time? All right. Again, I've got it right there. Yep. I think this is the way to look at it. Take this grid again, and all the galaxies are expanding from all the other galaxies. So we're not at the center. If we were an Andromeda, looked out, we'd see the same thing. Anywhere in the universe where all the galaxies will be expanding away from us. So it's exactly what Lemaitre had predicted. And
Can I ask a question? I'm missing a bit of logic and it might be very obvious, but each galaxy is also interacting with other individual galaxies.
Yes.
So how is that affected by this?
Well, it's affected if they're fairly nearby, right? The gravity of the galaxies overcomes the total expansion of the universe.
So they should be moving closer while the greater space.
That's right. And Andromeda, in fact, is doing that. It's moving closer to us and will collide with us in about 4 billion years. All right, and we see galaxies colliding. So locally that it takes over.
And what was Einstein's main rationale for rejecting this concept?
I don't know what Einstein's rationale for. Einstein thought that before Hubble's result, which was published in 1929, Einstein thought the universe was static. And I'm not quite sure what the problem he had with Lemaitre's thing, but he also retracted that and they became very good friends and he had high respect for Lemaitre. But I don't know the total history and I've never seen it totally laid out, but somehow Einstein's enormous intuition about science seemed to have left him a little bit in this thing, maybe because he really wasn't an astronomer, but I don't know. Anyway, so that's how the universe expands. Okay. Yeah.
One more question. I mean, when you think about the universe without the galaxies, is the universe also expanding or is there a limit?
Without the galaxies?
Yeah, without the galaxies. Nothing has to be something.
Yeah.
I'm
no.
talking about the space between the galaxies.
No, if there is a model, I mean, if you can theoretically model this, and if you take all the mass out of the universe, it expands differently from the way it really does. If that's your answer.
Okay.
Okay.
But there's no,
And-
there's no end to that yet.
We don't know the future.
Right.
And we don't know if that expansion will continue in the same way forever. We do know that in the past, that expansion rate has not been the same. It has changed. So and the future is that's very much a problem for us. We don't know what the future expansion rate will be. All right, so okay, so I'll try to illustrate this again. Suppose you're observing at this corner here and you observe two galaxies. And when the universe expands, you can see this galaxy moved this far, but the distant one moved further. And that's why we see the Hubble expansion. The velocity is proportional to the distance. And that's what Lemaitre had predicted. In fact, there was a movement a few years ago to change it from the Hubble constant. Let me get to the Hubble constant first and mention it. This is Hubble's diagram of the galaxies that he observed. And he plotted their speed. It's a sort of mistake here, it should be kilometers per second, versus their distance from us. In the astronomy parsecs business, which we don't, which we're not using here, but it's equivalent to light years. A parsec is 3 light years. So you can think of this as light years. And you see it's kind of a straight line. So velocity is proportional to distance. A lot of people criticize, say that, well, without the lines, it's not that convincing, but and maybe it wasn't, but Hubble published it, and it turned out to be absolutely right. This is how galaxies move. Okay, now this cat means that you don't have to follow this if you don't want to. This is just a little bit of extra I threw in. The way we get the velocities is that if you observe the wavelength of one of those lines and subtract the wavelength which you measure in the laboratory, divide it by the wavelength in the laboratory, that's the velocity divided by the velocity of light. So that's just for people who want to go a little bit further. Now, I also mentioned, because it'll come up in slides that I take from NASA, this Z. And Z is the observed minus the velocity. The same thing is up here. The observed minus the lambda velocity, the wavelength velocity, divided by the wavelength of the zero velocity. And astronomers use the Z all the time because it's an observable parameter. It doesn't depend on any theory. It's just directly what we observe. Okay. And Hubble then published this and it's called Hubble's law, that the velocity, this is the distance, this is the velocity. The velocity is proportional to the distance. To make it equal, you have to have a constant number. And that is Hubble's constant, which we measure from the galaxies that we see. It's called Hubble's constant. Now this gets a little more complicated when we go to very high distances, but I'm not going to go into that. And this is the famous relationship that the universe is expanding. That changed everything in astronomy. Ever since 1929, this has been the basis of our understanding of how the universe works. There was a movement a few years ago to call it the Hubble-Lemaitre constant, to give Lemaitre credit because he actually was first, theoretically, but that didn't take off, and it's just called the Hubble constant. Here's a more recent Hubble diagram, which shows the millions of light years here and the velocity in kilometers per second. You see it makes a really nice straight line. And the red spot here is the region of Hubble's measurements. So you see we have vastly better data now and much more accurate data and over much, much greater distances. And that's the Hubble constant. The parallel lines here show the uncertainty, and we don't always know the distance very accurately. And so the parallel lines are to indicate that uncertainty. Okay, so the universe expands. It looks like we don't need the lambda. And this is Lemaitre when he visited Einstein. I think this was actually taken at Caltech. And Einstein respected Lemaitre a lot. He did a great many things. But just for lecture 5, the lambda isn't dead. It came back again. So, but in a very interesting way. So just to remember that. All right. So well, one more way to think about it is that the whole universe expands, and it's like raisins in bread. People are in a cake. So I couldn't get that right. I mean, here I had to get the raisins expand too when you did that. But you get the idea. The galaxies don't expand. All right. Let's take a break for a few minutes.
So Ryan,
Yeah.
in that last example though, but there is no center.
There's no center.
I mean, there's a center to that thing.
Yeah. Any example I make.
Ungraspable.
Yeah.
There's no center.
And I don't mean to kind of dismiss it entirely. Because does the universe go on forever? Is it infinite?
Yeah.
Maybe it curves on itself. It could be complicated. One way you could think of it is that an example that's often given, although I didn't, is imagine spots on a sphere, on a
Right.
balloon.
Right,
Now, like the balloon expands.
right.
Now, that doesn't have a center in the dimensions of the surface of the balloon. It has a center else in a third dimension, but not there. That's another way to think of it.
Yeah.
Roger? If the universe is expanding, that energy that caused the expansion came from somewhere, which would be the Big Bang. Right?
Yeah.
But the farther it gets out, it rather than expanding faster, shouldn't it start to expand?
Mention historical event. Up until about 1965, there were differing views of the history of the future of the universe. One view was the one that I described. I mean, everybody saw that the galaxies, that the universe is expanding. But in terms of understanding that, there were two views. One was the Big Bang view, that in fact, that is what happened, that there was an initial event which caused the universe to expand, and we're still seeing that expansion. The second was that the steady state theory, you may have heard about, and that is that the universe never changes. It has no beginning and no end. And now they had a slight problem, the steady state people, because as if it's not changing, but the galaxies are moving apart, then the universe must be changing because it's getting less dense. And to get around that, they said, well, new galaxies are appearing in the empty space in between. And then people said, well, that doesn't conserve energy. Where does that come from? But the steady state theories had an answer to that too. If you propose a beginning to the universe, where did that energy come from? So that doesn't conserve energy either. I'm not sure that's completely resolved, that issue, but anyway, the term Big Bang was coined by Fred Hoyle, who was a proponent of the steady state theory, in fact, an inventor of it. And he was on a radio program in 1949 and was discussing the 2 points of view. And he described the steady state universe, and okay. He described that, and then to describe the expanding universe idea, he coined the term, it's like a Big Bang. It goes off. And so he was the one who coined it, even though he wasn't a believer at that time in that point of view of the universe. often it's been said, and I've read, that he was derisively referring to it, but Hoyle insists that's not the case. That he said in 1949, when all we had was radio, I had to try to be as descriptive as I possibly could because people weren't seeing anything. And Big Bang is the term that I came up with. And anyway, even though it was a steady stater who coined it, that term was so great that everybody has accepted it ever since.
Roger,
Yeah.
would you consider going back a couple slides so you can take credit for something?
Pardon me?
Could you go back a couple slides and just take credit for something? Yeah, right, whoop, one more, right there.
Yeah.
Okay.
Okay.
You notice the initials on this cartoon?
Well, I got curious as to how people say it. In Spain, Italy, and French, apparently they gave up and just call it the Big Bang. The Japanese also call it the Big Bang. Somebody speak Japanese or Chinese? Can somebody say? Yeah, how about Chinese? Can somebody say that? Nobody? Anybody Russian can? This is Big Bang. I can see that, but I don't know how that's pronounced. Yeah. The Germans call it große Knall. No, Urknall. So that's his cool. And the Latin, I made that, I looked that up. And so the Romans didn't really say that. But the one I really like is horrendous space kablooey, which hot and hopsy. In fact, again, a few years ago, the magazine Sky and Telescope said, could we think of another name for Big Bang? And everybody was invited to send in names, and I guess a lot of people did. And they said none of the names is as good as Big Bang. So the contest didn't go very far. All right. Now, notice also another thing, that we look back in time when we look out in the universe.
It keeps
Yeah.
popping back. Just
Okay.
hit play.
Ordinary computer. And so if you see a light photon, light is sort of particles, and from two different galaxies, the light approaches here, but it takes time to get here. So we see this galaxy as it was. And this one we see takes even longer, so we see it even earlier. So it takes, okay, now this is kind of cool. Make it work. Okay. Now this is how happens when we see light from a distant galaxy in the expanding universe. Now, my expanding universe has a boundary because I can't do anything but to show it, but it really doesn't have a boundary. Okay, so this is how it happens. Okay, the universe expands, light goes through it, and finally we see it. And it's redshifted. Frequency is shifted. Okay, so that's how. I don't know if I can. Yeah, I can. So that's the light photon that goes through. So you see, you have to think about, it's a little complicated. We're not used to that. It's like a runner racing on a racetrack, but the racetrack's expanding as he runs, so it's a little tricky. All right, if you see an image, again, it's the image comes to us.
Shouldn't that baby be older?
No, see, it's the image of the baby that we see, not the baby. The person on that distant galaxy does get older. I learned how to do this, and I got kind of carried away. All right. You want to see that one again? Here it comes. See, I didn't know how to make the woman get older. So anyway. All right, so what is this Hubble constant? The number that we have now is 21 kilometers per second per million light years, whatever that means. It means that for every million light years from us, the galaxies are faster by 21 kilometers per second, which is a pretty fast speed, like 76,000 kilometers per hour. So things are really moving out there. Okay. That's the Hubble constant. Now, again, and this is something you don't need to follow if you don't want to. Astronomers generally use kilometers per, there's a range here, 68 to 72 of kilometers per second per megaparsec. Again, astronomers use the parsec, not the light year. And if you look anything up, and some of the slides from NASA that I'll show use the parsec term, so that's what it is. But you don't need to worry about it too much. Now, there is a tension here, a problem. There are more than one way to measure the Hubble constant. And they don't give quite the same answer. And this is now, it's not, as far as we can tell, that somebody's doing it wrong. It seems that there's something going on.
So it's a relative constant.
So, okay. Oh yeah, here's, I did get carried away. Here's how the wavelengths changes. See, and the wavelengths gets longer as the universe expands. Okay.
By the redshift.
And that's the redshift. Okay, I couldn't make it red, you know, but anyway. But there's another thing about this. So the way I think, a better way to think about the redshift, I introduced it as Doppler shift because that's familiar to us. But a better way to think of it, I think, is that the wavelength of the light is stretched with the stretching of space, with the expansion of space. Okay, so we don't have to worry about the velocity of that galaxy. I mean, it does tell us that, but it's really more what happens in space as space expands. Right? And there's another point to think about here. When you talk about distance, and we did talk about distance, and the Hubble constant is calibrated on distance, but distances aren't the biggest thing that we need to think about. I mean, when you think about the distance to a galaxy, what do we actually mean? Do we mean the distance now, or do we mean the distance when the light left us, or something in between? Astronomers actually deal more with the redshift itself, with the amount of the wavelength shift of the light. That's the thing that we measure. Converting that into distance always involves some calculation, some theory, some thinking about the universe. So it's a less direct thing. The direct thing is what you just measure at the telescope, and that's the redshift. And that's that Z, and you'll see it in some of the NASA slides, as I mentioned.
Rob, is that because as soon as you calculate it, it's wrong the next second because it's expanding?
Well, that's true too, yeah. But it's that same idea that, you know, when am I interested in the distance to that galaxy? Now, in the future, when the light left? Okay, and that's not the critical thing. The critical thing is how that expansion takes place. All right, so again, I said that this Z is just this. It's a for this one here, this example, it's this line goes over to here for a moving one. That's what we can calculate, the observed versus the zero velocity, what we see in the laboratory, and that's that Z. And the other thing about Z, I'll just mention it, is it actually tells you, I'm not going to prove this, but it actually tells you how much the universe has expanded since the light has left. Okay, and if we get a Z of a big Z like 10, it turns out that since the light left to us and we see the Z equals 10 galaxy, the universe has expanded 11 times in its size.
Roger, if the light wave is expanding because the universe is expanding, I'm imagining that we are holding opposite ends of a slinky. And as I walk away, they're going to be longer. Yours, where you're holding it, it's still going to be fairly dense. But the part that I'm taking away is gonna stretch out more and more. So the light, the wavelengths as it shifts, it's shifting more, it's more evident the farther away you get. But if you start about the origin, it's still fairly close together. You see what I'm saying? If it's switching because the universe is expanding, does that mean that the wavelength is longer at both ends equally, or is it longer at one end than at the other?
It's longer at one end than the other, if I understand you.
Yeah.
You're right. It starts out short wavelength.
Yeah,
And then as it moves through the universe, that wavelength expands, and by the time it gets to us, it's a longer wavelength.
right, but if you then took a picture in time of that entire wavelength from one end to the other, it would be shorter at one end and longer at the
Yeah,
other.
but we don't think of it that way because light comes as particles, as
Right.
photons. So it doesn't have a tail that's still sticking into the galaxy from where it starts out. Okay, a good question though. Okay, now, so we can now infer some other things. If the universe is expanding, okay, we see it expanding. And if we pretend that it didn't change, the speed didn't change, then we can calculate how long ago was it when the galaxies were touching, right? I mean, they weren't really touching, but you know what I mean. Okay, so the Hubble constant actually gives us a direct measurement, estimate of the age of the universe. And when you do that, you get that you get this 13.8 billion years. But what you actually get, and I mentioned it here, if you just take the best value for the Hubble constant we have right now, you get 14 billion years. Okay, and we say it's 13 billion years because we now know that the expansion was not always uniform. We have to take that into account. I won't go into that. 14 is close enough to 13.8 for anybody, it seems to me. Right? So that gives us the age of the universe. And it's consistent with other things we know. I mean, the Earth is 4.4 billion years old. So the universe is older than the Earth, which is good. The oldest stars we know in the galaxy, relatively nearby to us, are these globular cluster stars. They form in these giant clusters. And this one is 11.7 billion years old. It's M13. It's a fairly dramatic cluster that amateurs can see. The globular clusters are clusters of stars which form a roughly spherical thing around our galaxy. So this is just invented just to show you what it might look like. And in these clusters, there's a couple hundred of them that we know about around our galaxy, and other galaxies have these globular clusters also. And they're the oldest stars that we know about. Here's 4 pretty dramatic clustered globulars in our galaxy.
When you see sometimes the picture that the Hubble has taken, there's lots of pink and blue. What are those colors from?
Well, those colors are different wavelengths of the infrared light. From the JWST, it doesn't show any visible light, but they're trying to get us to thinking about it and see that there are different wavelengths of infrared light. Okay. Yeah, okay, I'll take 1 or 2 more questions and then we'll go on because it's getting late. Yeah.
There was something in the news about as the Hubble, not Hubble, but the other, that's like the Webb telescope sees further and further. There's some theory that maybe that beginning of the universe is not true. Is that still a theory or?
No, there was a beginning of the universe, but what actually happened in the beginning of the universe, those first few 100 million years, that is the JWST Webb is showing us that we didn't predict that correctly. That there are more interesting things happened and things that we haven't really understood yet, but we need to do a lot more observations to really see what's there and how what happened. Okay, I'll just take, you had a question and I'll go on from.
I was just wondering if there's any convention, any consistency in the way they assign false colors to the infrared when they present those images.
Not as far, I don't know the answer to that. If there's, the question is there consistency in how they do those colors. And you'd have to ask NASA that. They probably have some scheme, but I don't know what it is. Okay, well, here is exactly what may be relevant to your question. Here is looking really far back. The light here has traveled 13.4 billion years. And this is the kind of objects that we see, and we're trying to understand those. And they are quite surprising. They're small, they're very, very bright, luminous. I mean, for us to see them that far, surprisingly so. And they're red colors. And they have a lot of heavy elements like oxygen and nitrogen and stuff, which is surprising because we didn't think those formed that early. So there's lots of questions. We'll get to that, right? But it's just going ahead a little bit. All right, there's also this concept of the knowable universe. If the universe has lasted 13.8 billion years, nothing could have traveled longer than 13.8 billion years, right? And that's true even of a universe that doesn't expand, right? I mean, if the universe were huge, but had a finite age, 13.8 billion years, we wouldn't see anything further than that. So there's a region that we can know, but beyond that, we don't know what it is. Interestingly, appears to have been that Edgar Allan Poe, the writer and poet, was one of the first to point this out. People were very worried in the early 19th century, 1830s or 40s. They had a big question. They said, well, if the universe is infinitely big, and the stars go out infinitely far, then the whole sky should be bright, because no matter what direction we look, we'd see the surface of a star. Okay, but the universe is black, it's dark, except for where we see a few stars. And they were very puzzled by that. And what does that mean? And one thing it might mean is that the universe isn't infinite. But the other that apparently Edgar Allan Poe was one of the first to point out was that it means that the universe has a finite age, that had a beginning, that it's not infinitely old. So that's the limit. Oh, no, here, right? All right. So you see, even though the light traveled to us and took 13.8 billion years, say, the galaxy has continued going further away from us during that time. So this is what we call the horizon. It's the knowable universe, the furthest distance that we could even think about. And that turns out to be about 45 billion light years. So a radius from us. You see, even those distant galaxies that we're now seeing as they once were are now very much further away. So we still think we know something about them. And in that volume, the knowable universe, there are about 1 trillion galaxies. Okay, 1 trillion galaxies. And on the average, one of those, each galaxy has between, I don't know exactly what the average is, but something like 1 to 10 billion stars in it. Our galaxy has 200 billion stars, but we're a big galaxy. And so you take that average, that's how I came up with the number of stars in the universe.
Theoretically, couldn't you build a new space telescope that would allow you to see farther back than 13.4 billion years? No.
Not if the age is 13.8 billion years. Okay, well,
what would happen if you had a bigger telescope?
You keep seeing further and further back. And in fact, we do see further back. We see now events that took place in the universe when it was only 400,000 years old. And those events at 400,000 billion years, although reflect events that took place even earlier, seconds of when the universe was seconds old. But we keep pushing it back like that.
Regarding the Big Bang, did space exist and the Big Bang filled it with matter and energy, or is space itself created with the Big Bang?
That's
What's the theory on that?
I don't know the answer to that. Nobody knows the answer to that. Did time exist before the universe existed? Okay, that's what my friend in Hawaii keeps asking. We don't know the answer to that. Maybe time came into existence with the beginning of the universe. We're not there yet to answer those kinds of questions. I mean, it's a good question, but we're not there to answer. What we're doing is pushing things back further and further. That's how we'll know. And in a way, and without demeaning your question anyway, these are not new questions. People have been asking that for thousands of years. How did the universe begin? How did time begin? But we didn't make progress on that. I mean, a lot of important people, astrologers and priests and everybody argued about this and so on. But we didn't make progress on this until, you know, Galileo started measuring how long it took things to fall from a tower, or ground a tiny lens to look at the moon and see what was on the moon. That's how we started making progress on it. And so there are big important questions like, was there a beginning? How did it begin? All that. We don't know that yet. We're just pushing our horizons further back. Is that a good answer? I don't know.
Well,
Okay. And here now, I'm jumping ahead a little bit with this illustration, because this is the whole history of the universe, the whole everything. And it's what we're going to cover. But what you see here is an attempt to show, first of all, the expansion. That, you know, this is getting slightly bigger as time goes on. And the galaxies are here, and they come, and you know, there's first primitive galaxies, and then there's the galaxies in the universe that we know now. And it goes back to some things I haven't yet come to, but will. That is, when the first stars formed, the galaxies, close to the beginning. Then there was a period when there wasn't much, but before that, the universe was hot. And extremely high temperatures, no stars and so on, but things like atoms and photons were forming. It wasn't green, but that's just to show you. Okay. And there was a period of very rapid expansion. So we'll talk about all that. And notice also that that expansion is going a little faster recently. So that's another interesting thing to look at. Okay, and this is the Hubble, and it looked back to about that far, and the James Webb looks about that far. So it was built specifically for what it's doing now, to study how the first stars and galaxies in the universe formed. And that's what it's doing. And that's why we need a bigger telescope, infrared telescope in space. This is a NASA slide. Okay, well, there's a tension. And I put this leopard up just to show there's some danger in some of this. Actually, well, that's not really why. I wanted to show a slide from my trip to Africa last September. That was the excuse. I realize I'm reaching a bit here. Anyway, there's a problem. And that is that we discussed how to measure the Hubble constant from looking at galaxies, right? We determined their distance from the Cepheid variables, we determined their speed from the Doppler shift, and we get the Hubble constant. But there's another way to get it. And that is, if you look at the very early universe, and I'll just try to give you we'll talk about this in more detail later. If you look at the early universe, there's certain things that happened, and that would have happened differently if the expansion rate were different. For example, hydrogen converts to helium at very high temperatures in the very early universe. And we see that effect because everywhere you look in the universe, about 30% of the atoms are helium. And that formed in the early universe by number. Okay. That happened in the early universe. But if the universe had expanded faster, the universe would have cooled faster and wouldn't have gotten as much helium. And if it happened slower, then we would have gotten more helium than we see. So we have a measurement of the Hubble constant in the early universe. And if everything were okay, they would agree, but they don't agree. They're off by about 9%, the two methods. And that first showed up around 2010. And people thought, well, somebody's not made a mistake or not accurate enough. But the more people have measured it over the last 15 years, the more the errors have become smaller and the discrepancy has not become smaller. So now both measurements seem to be accurate, but they don't give the same result. So what seems to be going on is there's something about the universe that we don't know. I should rephrase that. Okay. But there's a lot about the universe we don't know, but there's something in our theoretical understanding. It appears. Most people think it's our theoretical understanding of the early universe, that there's something we don't quite get yet. There's still some people who think, well, maybe the measurements are peculiar in some way. Both could be a possibility. One possibility that's recently been in the news is that the observations of the Cepheid variable distance with velocity, that assumes the universe is smooth. But in fact, the universe isn't smooth. You know, it has these big gaps, these big holes, and then dense regions. And maybe that's screwing up the Cepheid calibration. And I recently discussed that with the astronomer at UCSC. Joel Primack. And he said that's all wrong, that idea isn't right, but I can't. All right, so I just want to leave you with that, I mean, the good thing about cosmology and astronomy in general is that you can bring people up right to the big fundamental issues. Easier, I think, than in physics or chemistry. The fundamental questions and the fundamental problems. And so that's one of them. All right, well, going back to Father Lemaitre, because he was a priest, people always asked him about, religion and cosmology in the beginning of the universe and stuff like that. And Lemaitre always left those questions out. He did not like to talk about those things. He had two different places, his faith and his science. He didn't want, but one time he did say this, and he said, as far as I can see, such a theory, meaning a theory of the origin of the universe, cosmology, remains entirely outside any metaphysical or religious question. It leaves the materialist free to deny any transcendental being. For the believer, it removes any attempt at familiarity with God. It is consonant with the wording of Isaiah speaking of a hidden God, hidden even at the beginning of creation. So that was Lemaitre's point of view. All right, so what do we take away from this? Galaxies recede from each other. There's no center. Galaxy speeds are proportional to galaxy distances. Galaxies are not moving into different parts of space. It's space itself that expands. The expansion rate gives an age of the universe of approximately 14 billion years. And distant galaxies allow us to study the early universe. So I think those are the fundamental takeaway points. One thing I want to make sure I get everybody clear, it's kind of beside the point, but when I talk about the Doppler shift, it's the Doppler shift of light, not of sound, right? We got an answer to an exam question once where the guy said we measure the distances to galaxies by listening to their Doppler shifts. So I don't want anybody to make that mistake. Yeah. Okay, this expansion is really the profoundest idea in the 20th century of astronomy. It remains our basis for our understanding of the universe. And even though our understanding is certainly going to change, and we're going to learn more, but everybody thinks that the expanding universe is still going to be the basis of any future theory or understanding of the universe. There's a nice quote from Hubble, which I think is the point. It's fun for me to show really photogenic galaxies and star fields, and everybody says, wow, but the real science is being done at those fuzzy little things that we barely make out, even with the JWST. And Hubble said, eventually we reach the dim boundary of the utmost limits of our telescopes. There we measure shadows, and we search among ghostly errors of measurements for landmarks that are scarcely more substantial. The search will continue. All right, next time we're going to talk about the cosmic microwave background radiation and the inflation of the universe. Okay, thank you. Pardon me? What are you looking for? Chairs outside.